today is Giulio Cerullo from Politecnico Milan. So Giulio Cerullo, he is really coming from Milan, he graduated there, and then he had there most of his career, apart from a stay in California, and any other place notable?
Mainly California.
Mainly California, the most relevant one. So, I mean, his research activity focuses on ultrafast spectroscopy, ultrafast optics, and in particular generation of tunable few optical cycle light pulses. And he applies this to the study of 2D materials, but one other research line in the group is also on DNA, so bio-related materials. So the technique is quite versatile. He has published tons of paper. He could not believe he has insert the number. So it's actually what is 1,322. It's true, certified by Scopus. So impressive number of citations. I mean, this is just to say that it's very well known in the field. Is one of the leading group in the world. So I mean, we are very happy to hear he has a lot of notable awards, which I will not list here. But what is most important that is here today to talk about his work on 2D materials and ultrafast spectroscopy. So I thank everybody present here. Thank also everybody online joining the talk. So you will have about like 45 minutes, and then we have a question and answer. And afterwards, there will be a border. So food and drinks for everybody. Thank you.
Okay. So thank you very much. Thank you, Zeila, for the kind invitation. I'm very happy to really start a strong collaboration with the Utrecht University. So first of all, I should say that with Zeila, we have a joint project. It's an EIC Pathfinder project that will start on the 1st of April. And this is already secure. And now we made a joint application for a doctoral training network with the Cross. If this also works. So we want to strengthen our collaboration. And both of these projects are focused on two-dimensional materials, so there is an obvious joint research interest. So as Zeila was saying, my research group mainly focuses on ultrafast optical spectroscopy, and I really come from the instrumentation side. So I like to build rather sophisticated optical setups and apply them to different problems. So one half of my research is on solids, and in particular on two-dimensional materials. In the framework of the graphene flagship project, I did a lot of fundamental studies on the optical properties of 2D materials. And the other half of my research is more on biomolecular systems, like we study DNA, we study photosynthetic complexes, still with this ultra-fast spectroscopy techniques. So in my lecture now, today, the outline of my talks is as follows. Zeila asked me to give a very broad general introduction to people who may not be familiar with the topic. So I will give an introduction on two-dimensional material from graphene to two-dimensional semiconductors. And then I will tell you about my own experimental result of non-equilibrium properties of this material. In particular, I will start with discussing excitons in two-dimensional semiconductors and their properties. Then I will talk about ultrafast spin valley dynamics in these materials. And finally, I will show you how one can put these materials really on top of each other, like in Lego bricks, and you can make heterostructures. And I will show you what are the ultrafast processes in heterostructures of two-dimensional materials. So let's start with the introduction on 2D material. So everything started with graphene, which is really the most popular 2D material. It is essentially a honeycomb lattice of carbon atoms bound by covalent bonds. So it's the thinnest material ever. It's a one-dimensional layer of carbon atoms, and it has remarkable electronic, mechanical, thermal, and optical properties. And even if it's a single layer, it still absorbs, compared to its thickness, significant. It is about 2.5%, 2.4% of the light is absorbed by graphene. So compared to its thickness, the interaction with light is extremely strong. Now, you have in graphene each carbon atoms, which has 4 electrons in the outer shell. 3 are sp2 hybridized and form covalent bonds, and the 4th is delocalized along the plane, so that graphene is a semi-metal with a very high conductivity. But now graphene has a remarkable band structure. So the bands in graphene are the famous Dirac cones, which touch at the Dirac point. And essentially, the charges within graphene move as, if you take the derivative of energy with respect to momentum, this will be like a linear dispersion relationship, and they behave like so-called massless Dirac fermions. Now, the other remarkable properties of graphene is that it interacts with light at any wavelength. So if you make a vertical transition between valence and conduction band, you can essentially absorb light at completely undoped graphene at any color, from the mid-infrared to the ultraviolet. So it is the only material which couples to light at every wavelength. And this is remarkable for many applications, like, for example, photodetectors. You can, in principle, make photodetectors with really broad bandwidth. Now, graphene has a lot of properties, but still it's a semi-metal that doesn't have a band gap. And it was initially essentially fabricated by just exfoliating a piece of graphite. So it was an extremely simple experiment. So then it was soon realized that graphene is not alone, that there is a whole family of two-dimensional materials, which are layered materials, which can be reduced to a single layer. And this gives a much richer physical behavior. So you have materials like boron nitride that are insulators. You have materials that are semiconductors, like MOS2, WS2. We will deal with them in detail. There are some materials that are even superconductors. So you can make layered materials with a really rich variety of properties. And what is even more interesting, as I will show you in my last part of my presentation, you can stack this material on top of each other by a van der Waals interaction, and you can really build artificial heterostructures without any lattice mismatch constraints, and again, you can get very rich physical properties. Now, in the general introduction, what are transition metal dichalcogenides? They are called TMDs, or somebody calls TMDCs. These are two-dimensional semiconductors that have the chemical formula MX2, where M is a transition metal. The most popular are molybdenum or tungsten, and X is a chalcogen, which can be selenium or sulfur. So, but these are just the four materials that I will deal with in my talk, but there are many more. You can really make hundreds of different materials, and they all have the same structure. So they consist of a strongly covalently bound layer, a layer of strongly covalently bound atoms, which is then held together with the other layers by van der Waals force. So they can be easily exfoliated down to a single layer. Now, the prototypical material is really a molybdenum disulfide. Here I'm showing you a single layer. You see the molybdenum atoms in the middle and the sulfur atoms at the sides. And here you have strong interlayer covalent bonds. And then each layer is held together with the others by weak van der Waals interaction. So if you consider, it's not really as thin as graphene, because now you have 3 layers of atoms, but still here you see an AFM, a single layer is 6.5 angstrom. So it's still, you can call it atomically thick material. And you can exfoliate it, but nowadays there are many techniques to make these materials. Of course, exfoliation typically gives you rather small samples. They can be of very high optical quality, but this is the Scotch tape method. You can grow them by chemical vapor deposition. They typically tend to form these triangular islands, and there you can cover really large areas with the material, but these materials have more defects. You can have different kinds of defects that Zeila is studying quite in detail. And then you can also have liquid phase exfoliation, where you can make so-called inks of this material. So you start on the bulk, and you, by doing ultrasonication, you can exfoliate maybe not single layers, but mixtures of multi-layers, but then you can make really large amounts of these materials. You can make so-called inks, which have many technological applications. So you can make these materials by several techniques. But now I want to focus on the really remarkable electronic and optical properties if you compare them to a standard semiconductor. So the first striking property that you have is that you have strongly bound excitons. So if you consider a normal semiconductor like gallium arsenide, you have, if you excite an electron from the valence of the conduction band, in principle, you leave a hole behind, and you should form what is called an exciton, which is an hydrogenic system where the electron and the hole are attracted. But in a bulk, in a three-dimensional semiconductor, there is a high dielectric constant of the material, which screens the interaction, the attractive interaction. So the binding energy of these excitons is extremely low. It's on the order of maybe a few milli-electron volts. So this means that at room temperature, the excitons do not exist. So at room unless you go to really low temperature, you don't see excitons, but you just see free carriers. Now here, when you go to a 2D material, you have two effects. First of all, you have a quantum confinement. Now you are confining the material in thickness. And then if you look now at the field lines of the excitons, you see that most of them are lying outside the material because it is so extremely thin. So the screening is also strongly reducing. So the combination of confinement and reduced screening dramatically increases the binding energy of the exciton, which now become a fraction of an electron volt. So you really have binding energies of maybe 0.2, 0.3, 0.5 eV, which are, even at room temperature, the excitons are very clearly visible and dominate the optical properties of these materials. And in fact, you can see them very clearly, even in room temperature conditions. Here I'm showing you the absorption spectra of the most popular of these dichalcogenides, MOS2, MOSC2, WS2, WSC2. In all of them, you see these very strong peaks. Now I will explain why there are these A and B excitons, but you really see these excitonic transitions very clearly at room temperature. So this is the first remarkable property. Now, another remarkable property is the fact that, you know, in a semiconductor, you can have a direct or an indirect band, depending on whether the minimum of the conduction band and the maximum of the valence band are at the same momentum, at the same wave vector. So in indirect band gap, you are not like silicon is an indirect band gap semiconductor, and it doesn't emit light very efficiently, while gallium arsenide is a direct band gap, and it emits light very strongly. Now, the remarkable properties of these materials is that when they are multi-layer, they are indirect band gap semiconductors. But when they switch even from a bilayer to a monolayer, the energy levels are rearranged and they become direct band gap semiconductors. So it's very easy to tell if you have a monolayer of this material from a bilayer, because if you do a photoluminescence, you will see orders of magnitude increase from a monolayer, from a bilayer, which basically emits very little, to a monolayer. Now, if you look at the band structure and the static absorption of these materials, you have two valleys, the K and the K prime valleys, which are energy degenerate. They have the same energy, and they are both, they both have direct transitions at the K prime point, and there is a strong spin orbit interaction that splits the valence band states. So the A and B excitons are really coming from this valence band splitting, which is on the order of 150 milli-electron volt in MOS2, and even higher in WS2 is on the order of 450 milli-electron volt. So this is the origin of these A and B excitons, the spin orbit splitting in the valence band. And then you have a third transition, which is the C exciton, which comes from vertical transitions in the gamma K band nesting region. Now, another remarkable properties of this material is our valley-dependent selection rule. Since you have the parity symmetry in this material is broken, so you have a locking of spin and valley index, meaning that you can selectively populate the K or the K prime valley by circularly polarized light. And so you can address selectively one of these valleys and you can create electron and holes that are spin polarized. So you have, in addition, in a way, to the electron and the spin degree of freedom, now you also have the valley degree of freedom. You can, in a way, control in which valley you put your carriers. And this has given rise to proposals to develop what is called valleytronics. Now you can use the localization of the bits of the carriers in a valley as a possible way to store information. So you have one bit in K and another bit in K prime, and this potentially could reduce dissipation. Of course, this begs the question to understand what are how long does this valley polarization persist once you have created. So you see there is a really rich playground, the rich physics just in the monolayers. Then if you combine them, it becomes even richer. Now, what is the technique that I use to study these materials? It's ultra-fast optical spectroscopy, in particular transient absorption spectroscopy. I will show you also other techniques. But the most general technique is relatively simple to understand. It's called also pump probe. So what do? You have two pulses, the pump and the probe, which are focused on the same position of the sample. And they are typically non-collinear, so they are propagating a different direction. So after the sample, you just measure your probe. And then you compare the transmission of the probe in the presence of the pump with the transmission of the probe in the absence of the pump. So you compare these two, and what you measure is the differential transmission. So the transmission with the pump minus the transmission without the pump as a function of the delay between the pump and the probe. And so with the pump, you modify the optical properties of the material. And with the probe pulse, you measure how these optical properties, how the transmission is reflected as a function after the pump has arrived. And the delay is really given by, the time resolution is given by the delay between pump and probe, which can be controlled very precisely by a mechanical delay line. So by scanning a mechanical delay line, you can change the delay between pump and probe, and you can control this, you can measure your signal. Now, how do you do this modulation? Typically, you switch on and off your pump. You have a series of pump and probe pulses, and every second probe pulse, you switch the pump off. And so you measure on, minus pump, probe with pump on, minus probe with pump off, and you repeat until you get sufficient signal to noise, and then you move to the next delay. So this is how the experiment works. Essentially, you have these two sources, these two pulses, which can be pretty short, and actually it's our specialty to make really short pulses to the order of 10 femtoseconds or even shorter. And we measure on the same, we change the delay between pump and probe from positive to negative. And what we measure is what you see here, is a map of the differential transmission of the probe. Here you are measuring a spectrum, because typically we resolve the probe colors on a spectrometer. And here you see in time the delay. So what you can do is, once you get this map, you can say, okay, I sit at a given delay and I look at my spectrum, or I sit at a given probe frequency and I look at my dynamics. So this is the general technique that we have developed over the years. Of course, there are many laboratories that use this transient absorption because it's very powerful, and it gives you a lot of information on the non-equilibrium properties of the system. And now I will show you several examples of application to the material. So I will start with a very fundamental question: is what time does it take for an exciton to build up in a 2D material? This was work that was done by Chiara Trovatello, who was a PhD student at the time when she was visiting Jim Schack at Columbia University. Now Chiara is very successful. She's now a Marie Curie Fellow at Columbia University. So the idea is once you, if you go above the band gap of this material, you create free charges. What is the time required for these charges to feel the reciprocal attraction and to build up the exciton? Now, the idea is quite simple. So we have here you see the A and B excitons. Here you have the electronic band gap where you have essentially free charges above this. And now the idea is that we will use very short pulses on the order of 20 femtoseconds, and we will tune the energy of these pulses over a very broad range from the visible all the way to the ultraviolet. So we will give a lot of excess energy, and we will monitor the rise time of the signal, of the so-called bleaching signal of the excitons. Now, if we start with a pump in resonance with the exciton, so it is 1.95 eV, so in resonance with the A and B exciton, we see that the signal rises, here you see as a function of time, rises almost instantaneously within, let's say, 20 femtoseconds, which is about the duration, our temporal resolution. So we can say that if we pump the excitons on resonance, as expected, the buildup of the excitonic bleaching is instantaneous within the time resolution of the experiment. Now, what we can do is we can progressively increase the energy of the pump pulse. So we can give progressively more excess energy to this to our pump. And we look at still at the buildup of the exciton, and we see that now it clearly becomes slower. There is clearly now a rise time, which reaches about, for 2.75 EV, reaches around 30 femtoseconds. So now we can go even higher. We can really go to the ultraviolet. We can pump at 375 EV, and we see that the rise time is more or less above a certain threshold, remains more or less constant on the order of 30 femtoseconds. So we can really make a graph of the build-up time of the exciton bleaching as a function of pump photon energy, and we see that it rises until it nearly saturates to something around 30-40 femtoseconds. So to understand this, we asked the collaboration of the group of Andreas Knorr in Berlin, who modeled our experimental results, considering that the bleaching signal comes as a mixture of coherent and incoherent excitons. So the coherent excitons, of course, are formed instantaneously, while the incoherent ones are delayed through a phonon cascade. And with this model, and using parameters of the materials, this could reproduce quite well our experimental result and our pump energy dependence of the exciton build. So we really can resolve, thanks to this high time resolution, this very fundamental process of building up of the excitonic bleaching. So this is the first experiment. Now I want to show you ultra-fast spin valley dynamics. So as I said, you can use circularly polarized light to selectively excite one valley. For example, we can excite the K valley. Now, what can happen is a so-called inter-valley scattering process. So you can have, of course, population equally distributing among these valleys. And we want to measure how long it takes for this process. So for how long the polarization remains in this valley. So what is the technique that we use? We can use two kinds of techniques. So the first is what is called the time-resolved Faraday rotation. So the idea is that we have a pump pulse which is circularly polarized, so that creates electrons in one valley, and these electrons are also spin polarized. Now we come with a linearly polarized probe, and we measure the rotation of the polarization angle of the probe. And this rotation is proportional to the difference between the populations of spin up and spin down carriers. So if the spin up and the spin down carriers are equal, there is no rotation, so we will see zero signal. If there is more one valley, we will see a positive signal. If there is more of the opposite valley, you will see a negative signal. So, and this measurement can be done really sensitively with what is called, if we use a Wollaston prism increase the two orthogonal polarization and a balanced photodetector. So this is similar to what is used in terahertz detection. You can really make very precise, very noise-free measurements. And so this is what we did on MOS2, but now we have repeated it on a number of materials. And actually, we see here the signal, the Faraday rotation. So first of all, we do a sanity check. So if we pump with sigma plus, we see a positive signal. If we pump with sigma minus, we see a negative signal, as we expect. If we pump with linear polarization, which is the sum of sigma plus and sigma minus, we are exciting both valleys simultaneously, so we see almost zero signal, so that's fine. And now we look at the dynamics. So we see that, first of all, there is a very fast relaxation with a time constant on the order of 200 femtoseconds. And so within 200 femtoseconds, most of the valley polarization is lost. We lose probably like 80–90%. And then there is a slower decay with the time constants maybe on the order of 5 picoseconds. So we can confirm this result with a different measurement, which is time-resolved circular dichroism. So what do? We do a pump probe. In this case, both pump and probe are circularly polarized, but now we have the same helicity or the opposite helicity. And these signals, in one case, we pump one valley and we probe the same valley. In the other case, we pump one valley and we probe the opposite valley. So if we look now at the dynamics, you see that same and opposite at time zero, they are clearly different. And you see there is a clear difference which is expected because of this essentially valley selectivity. But then as time passes, after 1 picosecond, the difference is very small, and after 5 picoseconds, the difference has disappeared. So there is a loss of this valley memory again within a few picoseconds. And again, we can measure, if we integrate this spectra, the difference of this spectra, we get a signal that has a very fast decay on the order of 100 femtoseconds and a slower decay of a few picoseconds, which is very similar to the previous result. So what is the valley depolarization mechanism? So here we didn't really make a one-to-one comparison of our experimental data with theory, but if you look at the theory, you see that there is this so-called exchange mechanism, which is a virtual recombination of a bright exciton in K and the creation of an exciton in K prime. Now, this is supposed to be a very efficient mechanism. And indeed, according to the parameters, they predict a very fast valley depolarization due to this exchange inter-valley electron exchange interaction on the order of 100 femtoseconds. And then there is a slower decay on the order of a few picoseconds. So in very good agreement with what we observe experimentally. Now, let me go back to this issue that the valence and the conduction band are there is spin-orbit interaction, spin-orbit coupling. So they are split. There's a strong splitting in the valence band and a smaller splitting, almost negligible, 1 order of magnitude smaller or even less in the conduction band. But what is very interesting is that if we look at these two materials, we see that there is a clear difference. For example, in MOS2, if you pump the A exciton, so you start here, for example, you have to conserve the spin. So you go here, and now the opposite spin has higher energy. But here in WS2, you pump the bright exciton, you go here, but there is the opposite spin has lower energy. So the spin ordering in the conduction band is reversed. So here you have what is called the dark exciton. You have a state which is at lower energy, which is dark, which you cannot access it because you need a spin flip. So how can you see this dark exciton? This is acting like a sink. So once you create the bright exciton, it goes to the dark exciton. So in fact, if you look, essentially you see in WS2, the dark exciton has lower energy than the bright exciton, while in MOS2 it has higher energy. And indeed, if you look at how the photoluminescence goes with temperature. In all, normally in a semiconductor, you expect that the lower the temperature, the more it emits. So in MOS2, that's what happens. If you decrease the temperature, the quantum yield increases. But in WSC2, which has this opposite spin ordering, if you decrease the temperature, the photoluminescence decreases. Why? Because you are trapping into this lower exciton and you don't have enough thermal energy to escape from this trap. So you end up in a state that doesn't emit. So what we wanted to measure is how long it takes for the spin to flip. And how do we do it? We have to do a rather, we want to measure the spin flip time. We have to do a rather sophisticated experiment. So we have to pump with a circularly polarized light and we access the A exciton. And then if we probe with the same circular polarization, but now looking at the B exciton, we will essentially only see a signal when there is this spin flip. So this signal will not be present at the beginning because we have not touched this transition. But as soon as we fill in there is this spin flip, we will see this bleaching signal rising. So we have to do a two-color helicity resolved pump probe. That's what we did. And indeed, we start with the one color and we see the usual instantaneous rise and decay. But now, if we tune here, we see that the rise is clearly much slower. At least if you zoom in, you will see it very clearly. Instead of rising instantaneously with our temporal resolution, it has a delayed rise of about 200 femtoseconds. So we say that this delayed rise is corresponding to the time that it takes for the spin to flip. And okay, if you look at the temperature dependence, you see that it becomes faster, this rise, as you go to room temperature. So it's a phonon-mediated process. And now here we have, we asked our collaborators, the group of Andrea Marini and Davide Sangalli, Luca Virs, I think the group here knows them all very well. So they did simulations according to the model, and even if there is not a quantitative agreement, they measure a slightly longer time constant, but they also see this spin flip on a picosecond time scale, and they also see a clear temperature dependence. So there is a very good qualitative agreement on the time scale and the temperature dependence of the spin flip process. So the last thing I want to show you about the spins is, sorry, what happened? Okay. Sorry, is this experiment, which is an experiment that was motivated by theoretical work done by Misha Ivanov at the Max Born in Berlin, and it was done by my very bright PhD student, Francesco Gucci. Now, there came out about 1.5 years ago, 2 papers almost simultaneously that were predicting that you could achieve ultra-fast all-optic Valley polarization switching in transition metal dichalcogenides. So what is the idea? The idea of this experiment is that if you use 2 pulses with perpendicular polarizations and you control their delay with interferometric stability, meaning that you need to control the delay with a precision much bigger than the optical cycle, which is 2 femtoseconds in the visible. So you need attosecond precision in the delay. Then you can really modulate the Valley polarization. Here is the measurement of the Valley polarization, which oscillates with the carrier frequency. In this case, 2 femtoseconds in the visible. And also using sequences of phase-locked pulses, you can switch on and off the Valley polarization. Now, it is not easy to make these perpendicularly polarized pulses with such an interferometric stability. You need a really stable interferometer. But we have a trick. We have an interferometer that we have introduced and patented for different applications of 2-dimensional spectroscopy, which we call the twins interferometer. And this device is based on a sequence of birefringent wedges of birefringent material. So what you do is essentially, by moving 2 of these wedges, you create 2 perpendicularly polarized pulses with really precisely controlled delay, and the delay is really parametrically stable, much better than an optical cycle. So this is the perfect instrument for testing this theoretical prediction. So I gave to my student the task to do the experiment, and it's not an easy experiment because you need, first of all, to generate the perpendicularly polarized pulse. You need to excite a single layer of this material. And then if you want to measure the Valley polarization, you need to use a Wollaston prism and do a balance detection with a couple of photodiodes. And actually, this is, let's say, how one expects with as a function of the delay of the two pulses, you should be able to modulate the polarization of sigma plus and sigma minus. So if you look at the Faraday rotation, you should really see this oscillation. And indeed, to my surprise, that's what our students managed to see. This is not a simulation, this is real experimental data. So you really see the Valley polarization oscillating with a period of approximately, well, this is really the carrier period, in this case is 2 femtoseconds. So you can switch between the two valleys, let's say, within less than a femtosecond, essentially by controlling the delay of these two pulses. And actually what you can do by using more complex sequences of phase-locked pulses, which you can also generate, you can, for example, here I am creating a Valley polarization, then I'm switching it off, and then I'm turning it on again. Or I can, in this case, I'm amplifying the Valley polarization. So you can really do logic operations on the valleys using these sequences of phase-locked pulses. So this is really showing how you can use this technique to control Valley polarization. Now, in the last 10 minutes, I want to move to heterostructures. Now, the power of these materials is that you can really stack them, each one on top of the other, doing mechanically assembled stacks, where you can really make sandwiches of these materials that are held together by interlayer van der Waals forces. And this is very different. In a normal semiconductor, you want to make an heterostructure, you need to be careful that the different materials have different lattice constants. So it's not easy to put two semiconductors on top of each other. But here, since you have this van der Waals interaction, you are really free to put, for example, one material on top of graphene and then make sandwiches of different materials. So you really have a very you don't have lattice mismatch limitations, and each material preserves its individual character, but now you can get new properties which are tunable according to the order of the materials, but also you have an additional degree of freedom, which is the twist angle between the two materials. So the layer band alignment, but also the twist angle is quite important. So it's a very rich field, these of van der Waals heterostructures. Now I want to show you just one example where you have a so-called type 2 heterostructure of two materials, in this case WSE2 and MOSE2. Now, MOSE2 has a smaller band gap than WSE2, as you can see. But they have this so-called type 2 band alignment where the maximum of the valence band is in WSE2 and the minimum of the conduction band is in MOSE2. So what happens in this case? Assuming that you create an exciton in MOSE2, you don't touch WSE2 because you are still below the band gap. But now you know that the hole always tends to float to higher energy. So what will happen is that the hole will have a very rapid transfer to the other material, and you will form what is called an interlayer exciton, where now the electron sits on one material and the hole sits on the other. And this has completely different properties. It has much longer lifetime. It can be transported over a distance. So it's a very interesting object. So what we want to do with our experiments is we want to visualize this process in real time, study the interlayer or transfer dynamics. We want to see how long it takes, again, for the interlayer exciton to form, and we want to measure the lifetime of these interlayer excitons. So the first experiment that we did was done by our postdoc Zilong Wang. This was done a few years ago when these materials were still these heterostructures were really hard to make. So we had very small materials. So the sample was provided by Deji Akinwande at the University of Texas. Here you see, maybe you cannot see the scale. I think it is 10 microns. So these are really small flakes on the order of 10, 20 micron, and they are mechanically stacked on top of each other. And there is an area where there is only the WSE2. There is an area where there is only the MOSE2, and there is an area where you have the heterostructure. And now you can measure the absorption spectra of this material. So you see at 9 Kelvin, the MOSE2, you have the A and B exciton. The WSE2, again, the A and B exciton. Now, if you measure the heterostructure, you see that pretty much you get the sum of the two. So you see the A exciton of one, the exciton of the other, B and B. So they are slightly redshifted because, of course, the dielectric environment changes when you put them on top of each other. But this shows that there is no strong interaction between the two materials, let's say, if you are in the ground state, not excited. Now, in order to study this material, we had to develop a two-color pan-probe microscopy. So we had to focus our ultrashort pulse to very small areas. So here I don't go into the details. So we can select one color for the pump and one color for the probe, and then we can focus both to maybe 1 micron. And now, what is our goal? Our goal is to pump only the low bandgap material, the MOSE2, and to probe at the A exciton of the WSE2, of the higher bandgap material. So what do we expect to see? Since we expect this whole transfer, we expect to see the bleaching only when the whole transfer is indeed happening. Now, the beautiful thing about our sample is that we can really select according to where we put our pump and probe. If we excite the MOSE2, which is the low bandgap, the WSE2, the high bandgap, or the heterostructure. And here we see completely different signals. Now, if we pump the MOSE2 and we excite and we probe at the frequency of the WSE2, we see a negative signal. So this is due to what is called bandgap renormalization, but it's a rather weak signal that is coming from the monolayer. Now, if we probe if we pump the monolayer of WSE2, we are essentially below bandgap, so we see zero signal. And this is again what we expect. But now, if we pump the heterostructure, we see a very strong signal, which is a bleaching of this, and this bleaching is delayed, is clearly delayed by a rise time of about 230 femtoseconds. So we really resolve the interlayer whole transfer process with a time constant on the order of 230 femtoseconds. Now, we can also look at the recombination time, which is much longer than in the case of the normal intralayer exciton. Is on the order of 1 nanosecond. Now, we can do this as a function of temperature from 9 Kelvin to room temperature, but we can see that the rise time is nearly constant on the order of 200 femtoseconds, while the decay time is strongly dependent on the temperature, and it goes from more than a nanosecond down to less than 100 picoseconds at room temperature. So now this shows that there is an energy activated type temperature dependence for the relaxation time, while there is no temperature dependence for the charge separation. So again, to understand these results, we asked the help of Oleg Presdo at the University of Southern California, who did non-adiabatic molecular dynamics simulation, and he could actually accurately reproduce the time scale of our dynamics. So he could reproduce that the interlayer Hall transfer happens in approximately 250 femtoseconds, and it is nearly temperature independent. And this temperature independence is explained by the fact that it occurs within a dense manifold of states and is driven by a high frequency interlayer phonon. And it can also reproduce the interlayer exciton recombination, which is has a strong temperature dependence. And this is due to the slowdown at low temperature is due to decreased non-adiabatic electron phonon coupling and increased bandgap. Now, in the very last minute before, I don't want to steal too much time from your dreams. So I just want to show you a very last step. Now we have seen the interlayer of separation. I want to see if we can also measure how long it takes for the interlayer exciton to form. This was work done by our very brilliant PhD student, Oleg Dogadov. Now, after these initial experiments, so the question is, what is the time really it takes for this interlayer exciton to form? And now we had a dramatic improvement in the quality of our sample, thanks to a collaboration with Xiaoyang Zhu at Columbia University, who introduced a gold tape exfoliation method and it can produce now really large area flakes of single layer materials. So now before we had like 10 micron heterostructure. Now we have heterostructure which are on the order of millimeters squared. So this makes our life much easier. We can do much more sophisticated experiments. In particular, what we can do is we can do again a pump probe, but we can do a pump probe outside the microscope where we can have a really broadband probe that covers simultaneously all the excitonic transitions. Before we only covered one color. So now we are pumping in resonance with the A exciton of MOSE2. And actually here now we see all the 4 excitons, even here the B exciton of WSE2. We can see the bleaching of all these 4 excitons. And actually we see quite nicely, even from this data, that the A and B exciton of MOSE2 rise nearly instantaneously with our pump, while the A exciton of WSE2 is clearly delayed by approximately 300 or 400 femtoseconds. And this is exactly what I've shown before. The interlayer of transfer takes a couple of 100 femtoseconds. And this is very clearly seen. But now what we can do is we can look at the luminescence of this heterostructure, which occurs, so the interlayer exciton is emitting in this range between 1.3 and 1.5 electron volts. So here, if we look at our signal there, we see almost nothing. But now, if we really, since we have a very high signal to noise, if we zoom in, it is not really zero. There is a very weak but clear positive signal. So this is really the signal of the interlayer exciton. And now we can do a dynamics, and we see that the interlayer exciton is formed with a time constant of the order of 1 picosecond. So there is you see that MOSE2 A peak is bleaching instantaneously. The WSE2 A peak is bleaching with a delay of approximately 100 femtoseconds. You can see it clearly, there is a delay, but a small delay. But now this interlayer exciton is very weak, but it has a delay which is on the order of 2 picoseconds almost. And so this is the signature of the interlayer exciton is further delayed. And here we can make a fit, and we get okay, now this is actually published, so I should you see the rise time of the interlayer exciton, you can fit it to something on the order of 1 picosecond. Again, we asked for the help of the group of Andreas Knorr in Berlin, and they could predict model quite well our experiment by considering that this interlayer hole tunneling occurs on a 100 femtosecond timescale. Then it leads to a hot interlayer exciton formation. Then this interlayer exciton thermalizes with phonons. And in the end, the species that emits forms within, let's say, 1 picosecond. So we can follow really all the steps of this charge separation and interlayer exciton process. Okay, so I had still, and I don't have the time to discuss this too complicated, the 2-dimensional spectroscopy. So I will just keep it and come to my conclusions. So I showed that you can really do a lot of experiments with a lot of insight into this material. So I showed you the buildup of the exciton of the Coulomb string in 30 femtoseconds in a single layer MOS2. I showed you rapid valley depolarization by electron exchange mechanism. I showed you intervalley spin flip in a material occurring on a sub-picosecond timescale. I showed you subcycle control of valley polarization. Then moving to the heterostructure, I showed you ultrafast interlayer charge transfer on the order of 100 femtoseconds. I saw I showed interlayer exciton formation on the picosecond time scale, and I didn't have to show you also two-dimensional spectroscopy is another technique which is more complicated and gives even more information. So with this, I'm finishing my lecture, but before I want to, I want to thank all the people who contributed to this work. So so first of all, my group in Milano, of course, who did all these experiments. Then a lot of people who gave us the samples, because in Milano we don't grow any samples. So the group, of course, of Andrea Ferrari at the Cambridge Graphene Center, the group of Frank Coppens at ICFO and Klaas Tilleroy, who was actually was meeting for lunch today, the group of Camilla Coletti at the Italian Institute of Technology, Deji Akinwande, and Xiaoyang at Texas, and Xiaoyang Zhu at Columbia University. And also very key for us was the collaboration with theoreticians. So the collaboration with Oleg Prezdo at the University of Southern California, with Marco Polini and Andrea Tomadini at IIT, and then, of course, here they are not, but the group of Andreas Knorr and Deborah Pretzel. With this, I thank you for your attention.
Thank you very much, Giulio. So now, if somebody has a question, this is the time. We are going to use the magic cube or as a microphone. So don't be shy. There is one. Should I? It's meant to be thrown at people. We can be gentle.
Oh, it's actually live, and I thought it was very.
No, it's live.
Thank you for the nice overview. I have a basic question about the first experimental example you showed. You talked about coherent and incoherent.
Yes.
So, can I ask what coherent or incoherent with what?
Well, I think they are essentially with the excitation. So let's say in one case, we are directly exciting the exciton population because we are resonant. In the other case, our pump is above bandgap. So we are essentially creating free carriers, and then they form excitons, but in a way they are incoherent because they are resulting from the scattering.
So let's say coherent and incoherent with respect to the incoming.
Incoming excitation,
Yeah.
yes, yes.
Okay, thanks.
Thank you. Daniel.
Yeah.
You want it? Do you have it? Or should I pass it?
No, you should pass it. Related to that question, you start with interferometric optical control of
Yes.
switching between
Yes.
two values. So it is a driven switching, but I saw that the amplitude of your switching decreased in time. Can you maybe explain why this is the case?
Yes, yes, because
it's driven, it would be constant.
well, it's essentially because of the electron. I mean, you can only it depends on the electronic dephasing of the transition. So you are with one pulse. In this case, you will create a polarization in the material, and with the other pulse, now you interfere with this polarization and you create the valley polarization. So as long as what you measure with this decay is essentially the electronic dephasing of the transition that comes out if you make a fit. It's on the order of 30 femtosecond, which is what you expect and what you get for the electronic dephasing of this excitonic transition at room temperature. So this is the decay, the reason why this valley polarization decays.
But I think if you drag it, you bring it every time back to the original state or not.
Well, but the point is that you are having a delay between the two perpendicularly polarized pulses. So when this delay is much longer than this electronic dephasing, then you cannot do this anymore, because essentially you cannot get this coherent valley polarization.
It's my turn to.
Yeah, you have to throw it. Almost there.
Sorry, I could hit you there. I'm not really into this field, but I was wondering, with these heterostructures, you also mentioned about dark modes and so on.
Yes.
Couldn't you excite those with, for instance, an electron beam? So doing electron energy loss spectroscopy on these materials?
Probably you could, yes.
Is that done?
I think, well, I'm not also an expert in electron microscopy, but I think it could be done. So essentially what we want to do is we want to understand the optical excitations and how they evolve in time. But of course, with electron microscopy, you can get the different kind of information. Yes, for sure.
There.
Maybe a clarifying question about the first experiment, I think, where you measure the time constant of exciton binding.
Yes.
You're talking about transit absorption in terms of like bleaching of transitions because states are occupied.
Yes.
So then electrons on holes, which are fermions, they combine into an exciton, which is a boson, and then it blocks exciton transitions. Can you explain a bit how I have to think about it?
Well,
how a boson blocks its own transition?
Well, it's essentially you can think of it like essentially a Pauli blocking. So of course you are exciting a certain fraction. You are creating a certain population of excitons, and this kind of blocks further absorption. This is one of the mechanisms of the nonlinearity. There are also other mechanisms that is like band gap normalization, that is line width broadening. So, but in general, the dominant mechanism is really this Pauli blocking, which you can see as a bleaching. Let's say simply you cannot put more, you cannot create more excitons. So you are reducing the number of the absorption from the material.
We think about it in that way, irrespective of whether it's a single particle state or multi-particle state in terms of blocking.
I think you can reason in the same way. Let's say even if you consider a molecular exciton, you will see the same. Once you excite it, you will see, of course, a bleaching signal, which corresponds to a reduced absorption, stationary absorption.
Yeah, maybe a bit of naive question. You started by saying that what makes this to be special is because you can isolate them to have a single layer, right?
Yes, yes.
But then the heterostructure, they also held by the same van der Waals forces.
Yes.
And then they still exhibit, the same behavior as a single layer. So I don't really get why then you still get this individual properties.
Now the point is that they, of course, the property of the heterostructure is very different from the property of a single layer, but the single layers by themselves, you can describe, I mean, they are not deeply affected by but then when you combine them, for example, you get this type 2 level alignment, and then, for example, you get this charge separation. So you can have, for example, other heterostructures where you put graphene on top of transition metal dichalcogenide. So you can really do a lot of combinations. And the nice thing is that you are really free to put the materials on top of each other without worrying that the fact that they have very different lattice constants. And then each one, for example, if you put HBN, which is a very high band gap insulator, in between, so you can use it as a sandwich. Let's say you sandwich between two HBN layers, one layer of this material. Then the two HBN remain essentially insulators, and this material is kind of protected from the environment. This is another example of heterostructure that is commonly used. So each material, I think, retains its individual properties, but then when you combine them, you generate new properties.
Roy? It's the weight of people.
You show that the interlayer exciton, the recombination is somewhat activated, seems like there's a small energy area.
Yes.
Can you clarify what's the origin of that?
Well, I think so we see that it's temperature activated, And there is I think there is an interlayer breathing mode that somehow activates these, and it has a frequency which somehow corresponds to an activation temperature in the range of maybe 100 Kelvin or so.
So for these heterostructures, is there an influence on the twist?
Yes, yes, very much, very much. Yes, there is an influence, especially when you go to this very small angle where you get the so-called moire effects. And well, we find in general that we have, for example, typically the referees ask us always to perform the electronical different twist angles. And unless you go to this really peculiar moire distribution, you don't see huge effects. But then when you go to this small angle where you get this, then you see really dramatic. We are still now, we have data there, we are trying to understand them because things change completely. But if you, let's say, if you are at large angles, we don't see a huge difference between different twist angles, yes.
Thank you.
Yeah, basically Ricardo is doing this kind of simulation, so I advertise his work. You see a shift of the exciton peaks and some extra feature will be better actually, but it's not trivial at all, so that's very...
So then based on the extra binding energy, you can determine twist angle. Sort of reverse.
That's the thing.
Well, yeah, the way to determine twist angle is if you do second harmonic generation and you do polarization dependent, you get you have a six-fold symmetry. You get kind of a flower dependence, and this tells you the orientation. And then, so if you put an heterostructure, you will see two flowers corresponding to the two material, and then you can tell very well. I have this. If you somewhere I must have these images, but okay.
That's one. Yeah. Thank you.
Yeah, so I have a, let's say, more general and applied question. So I know you've been working on these materials for a very long time, and you showed a little bit about this value polarization and how this can be used for even like value operations. My question is, how promising do you think is the use of optics and these TMDs for actually? Yeah, like what's the computing for things like this?
Okay, so this is a question that I get answered also because, you know, the European Union gave €1 billion for this graphene flagship, where graphene includes all 2D materials, and they want to see some result after 10 years. So, of course, many promises are not easy to fulfill if you look at electronic circuits or, well, I think graphene, I have in mind a couple of applications. One is you can put graphene, I must even have it somewhere, but you can put a graphene on, if you take a silicon waveguide, which is used in silicon photonics, you put graphene on top, and you can make, by changing, because graphene, you can couple the evanescent mode of the waveguide to the graphene. So even if graphene absorbs 2%, if you have a long path, you can extinguish completely your transmitted beam. But now, if you polarize the graphene, if you change, I don't know if there is
The table, on the table.
I saw them before. Yeah, okay.
Yeah.
Yeah, okay, yes. Okay, so let's say, so you have this transition now in graphene. Now, what you can do easily, you can polarize, you can apply a voltage to graphene, so you can fill your conduction band. And now this transition becomes blocked. So the graphene becomes essentially transparent. So you can make an electro-absorption modulator with graphene, and this can go up to hundreds of gigahertz. So this is an application which is, I think it can really be a product that can be commercialized for telecom applications. And there is another application in which I am involved, where graphene has essentially, if you think of it like it absorbs at every wavelength. So and what it does, if you absorb a photon, say, or if you come with a pulse of light, you create some electrons in the conduction band which thermalize very quickly. And then these electrons thermalize with the phonons. And this is a very fast process. So within approximately 1 picosecond, the electrons cool and the graphene goes back to its original situation. So essentially, if you come with a pulse in graphene instantaneously becomes more transparent because you are Pauli blocking, you are blocking this absorption. But then within a picosecond, it goes back to the original. And this is what is called a saturated absorber. So it's like a very fast switch. It closes, and then it opens again. And this is very useful in lasers because it can make the mode locking. It can generate pulses from the laser. And this can work at any wavelength. So it can work, for example, a 1.5 micron and 1 micron. So with my friend Andrea Ferrari, we have founded a spin-off company that wants to make a laser, a fiber laser, which contains graphene, to synchronize two independent lasers. And the result are pulses that are synchronized, and they are used for what is called the stimulated Raman scattering microscopy. And this is used, for example, for doing, you can look at vibrations. We use them on tissues, and really tissues from patients' biopsies, and we can do chemical imaging very fast. And actually, this is something that the laser is already a commercial product. We already sold these lasers. And so this looks quite a promising application. So there are a couple of applications in optoelectronics.
What about infrared detections?
That's another.
Also
Yes, I think Frank Oppens is working a lot on this with class also. You can really have broadband infrared detectors or even hyperspectral. So you can make really very broadband detectors, and then you can combine, of course, visible and infrared and do a lot of things. Yes, this is a big market. The other big application, of course, you have a material that is transparent, but is also a conductor. So it can replace ITO in all the screens. But again, then you have to see whether it's really more convenient. It's more I would say a financial issue. This is another application of graphene. So they are coming, the application of graphene. Application of TMDs. Then there are, of course, many applications. For example, I know there is a company, Diretta Plus, which is close to Milano. They make they make liquid phase exfoliation. So they make multi-layer graphene. And something that fascinated me, there was a lake somewhere where there was a spill of pollutants like petrol, I think. And so they put the graphene, and the graphene has a huge surface to volume area. So the graphene managed to absorb quite efficiently this pollutant. This is for then there is of course a lot of application in textiles, in other kind of exploiting different properties. But on the TMDs, it's still, I mean, maybe still needs a bit of time, but it's only coming.
They're also younger, so.
Yes, yes.
Okay. If there are no more questions, I was looking online, I don't see any raised hand online. So we can go to the bar here, and you can still talk to Giulio while I take the drink. So you're very welcome to come with us.